Why use significant figures? The purpose of this video is to provide another example showing why scientists use significant figures to communicate measured quantities. And I just want to open up a screen share here, so bear with me a second. I think we're good. I'd like a little marker to do that. So grab a spotlight. And I'm going to look at an example. I see three numbers, 5 miles, 5.0 miles, 5.00 miles. They all look like the same amount, and they are the same amount. But I'm going to use a story to highlight the differences in really the range of error that's communicated. So if I wanted to say, where do I live? I might say, go on Cedar, and then once you cross the river, go north 5 miles. Now, I don't know if it's exactly 5 miles, but I think it's at least 4, and I think it's less than 6, but that's about it. Okay, so that's not a very precise measure. This 5 miles means somewhere between 4 and 6, or I could say 5 miles plus or minus 1 mile. Here's another example. Back when I got married, I had to do directions to our reception. And in most of the people back then had cars with odometers that went to the nearest tenth. We didn't have all the GPS and navigation type things. And those are reasonably accurate. So you use that odometer, and I said, okay, you go to this street and then go 5.0 miles, because it wasn't 4.9 or 4.8 or 5.1 or 5.2. It just so happened to land on 5.0 before the next turn. So if you were driving there and you got to 4, you weren't really thinking that it would be there. But when you got to 4.7, 4.8, you started looking and you went past 5.2, 5.3. Hey, maybe we missed it. So really, when I said 5.0 miles, it was more precise, and you could maybe give it an error range of plus or minus 0.1. Notice the same number here is here, but implying less of an error range. And instead of saying plus or minus with every measurement, we imply a range of error with our numbers. Now, let's say I was going to sponsor a running race, and this running race was going to be a 5-mile race, and I was going to try to recruit some world-class athletes to that. And so if somebody ran really, really fast and they set a world record or a national record, we would want to give them credit and make sure it's, I don't know, tax certified or whoever certifies that nowadays. So it's going to be measured much more precisely, and that 5-mile run might be somewhere between 0.499 or 5.01, a very, very small range of error. So 3 numbers, all the same measure, but bigger range of error, medium range of error, smaller range of error. So instead of having to write plus or minus whatever our range of error is, there is an implied range of error with the numbers that we report. So 3 things about significant figures. The number representing a measured quantity should indicate the uncertainty or the range of error in that measured quantity. In general, the uncertainty of a measured quantity corresponds to the small scale reading of the instrument used to measure that quantity. In other words, next week in lab, we'll be using a graduated cylinder with increments to the 1 milliliter mark. So 1 milliliter will be approximately the range of error there. And then estimate one place past the small scale reading when making a measure. So if the increments of the graduated cylinder go in increments of milliliters, let's say I found it's between 32 and 33 milliliters, I might say 32.3 or 32.5 or 32.7, depending if it's closer to the 32 or 33 or right in between. All digits in a number are important. Significant means a measurement decision was made. And you might see significant figures, you might see significant digits, they're the same thing. You might see sig figs. I don't know if you'll ever hear sig digs, but I guess you can do that too. Okay, so let's just go to one more example down here. And you'll see that numbers, all non-zero numbers are significant figures because their measurement decisions were made. Here, you have 230.08. It's not 231, it's not 239. Zeros are sandwiched, those are significant. Trailing zeros in a decimal are significant. It's not 6.301 or 6.302 or 6.299, just so happens to be 6.300. Zeros that are not significant are placeholding zeros in numbers less than 1 right after the decimal, like the 0 and 0.006 is a placeholder, but it's not a measurement decision, and also trailing zeros in a whole number. And here's an example to highlight that. So nobody likes to take out our garbage in our house, probably including me. So I just thought, how far is it to go from the garbage can in the kitchen to the door? And I paced it off, and it did 6 good pace steps, and I would say it's 6 meters. I don't know if it's exactly 6 meters. I'm pretty confident it's at least 5, and pretty confident that it's less than 7, but that's about it. So this sig figs, this 6 meters is probably a plus or minus 1 meter. It only has 1 sig fig. Let's say I convert that to millimeters. Well, 1,000 millimeters in a meter, it would be 6,000 millimeters. Really, our range of error isn't going to change. It's going to be between 5,000 millimeters and 7,000 millimeters, and there's still 1 sig fig. It didn't get any more precise when I did that change. Let's say I go the other way. I take 6 meters and I say 0.006 kilometers. Again, I'm pretty confident it's between 0.005 kilometers, 0.007 kilometers, but the range of error is still plus or minus 0.001 kilometers, 1 sig fig. So are these zeros important? Yes, as placeholders, but they're not measurement decisions. Are these zeros important? Yes, as placeholders, not significant figures. What if I put a 0 right in front there? That really doesn't matter either for significant figures or placeholders, but when I write in text or something, or when I look up here, sometimes that 0 there just gives me extra clarity, especially when it's in a sentence. One final note is just going to using significant figures in calculations, and just want to do a little add-on with that. So I have a box. In that box, I measure very precisely the length and the width, but I estimate on the height. So when I do length times width by height to get the volume, even though I have 2 very precise measures, I have an imprecise measure. So my final volume reading is not going to be any more precise than that least precise measure. So always look for the least precise measure. That's going to limit things. When you add and subtract, look at place. This one's to the thousands place. This one's to the ones place. After I go through things, my final answer will be to the least precise or to the ones place. The least precise is tenths. My final answer is tenths. Least precise is tenths. Final answer is tenths. And least precise is the hundreds place. My final answer is to the hundreds place. When you multiply and divide, it's similar. You always look for least precise, but instead of looking at place like we did up here, you count the number of significant digits. This has 3, this has 2. My final answer would have 2 because 2 is less precise. 4 and 2 significant figures, final answer has 2. Remember, this one only has 2, this one has 3. Final answer would have 2. Adding, subtracting, look at place. Multiplying, dividing, look at number of significant digits. Always go to the least precise. I hope this video helps you understand the why behind using the significant figures. Please watch Mr. Brewer's and Ms. Sundberg's videos for specific instructions about counting sig figs, adding, subtracting sig figs, and multiplying and dividing sig figs.